Welcome to this lesson on radical multiplication and division. In this lesson, we learn how to multiply and divide radicals. So, unlike adding and subtracting, multiplying might be considered a lot easier because when you're multiplying, all you do is multiply the coefficients and also multiply the radicands. So let's just dive right into it by doing question 1, and you'll gain a better understanding of what I just said. So the coefficients, remember, are the numbers that are on the outside. For this first question, we have a negative, but remember this negative doesn't just hang out there on its own. There's an invisible 1 that's understood to be there. Also, for this second radical, there's an invisible 1 right there. So the coefficients are -1 times 1, which becomes -1. And then next, we will multiply the radicands. So root 3 times root 2 is simply root 6. And that's the answer to this problem. But just to be more, mathematically correct, we really don't show a coefficient of 1. So I would write this out as negative root 6 to be more mathematically sound. And now for question 2, we will continue practicing what we just learned from question 1. Once again, when you're multiplying radicals, you simply multiply the coefficients. Our coefficients in this case are 5 times -6. So that's just going to be -30. And then now we'll multiply the radicands. So root 2 times root 10 is root 20. However, for this question, we can't just walk away from it yet because the root 20 can be broken down further. In other words, we can simplify it. So let's just copy this question over here so we have more room to work with. -30 root 20. And really, we're focusing on the square root of 20 because that's what we need to simplify. Remember, when you're simplifying the radicands, you're looking for two factors. In other words, two numbers that when multiplied will equal 20. However, we don't just want any random numbers. One of those numbers has to be a perfect square. So what multiplies to 20? Let's go in order. 2 times 10. But neither the 2 nor the 10 is a perfect square, so that's not a good pair. What else multiplies to 20? We could go to 4 times 5. And look at that. This is our best pair because 4 has a square root. In other words, it's a perfect square. So we can rewrite it as -30 root 4 times 5. Now, the square root of 4 is a 2, and that, of course, is going to go on the outside. And when it goes on the outside, it has to multiply the number that was already there. So 2 times -30 is -60. And of course, we have the 5 remaining inside as our radicand because we can't break it down any further. So the answer to this would be -60 root 5. Now let's try the third question. In this question, you find that we are now dividing because we have square root of 1 divided by square root of 9. Now, one thing I do want to mention right off the bat is in math, you're not allowed to have radicals as a denominator. But we'll work on how to fix that when we get to question 4. For now, let's just work on this because we are lucky enough to have perfect squares for both the numerator and the denominator. Square root of 1 is simply 1. Square root of 9 is simply 3. So the answer to this third question is just 1/3. And now for the fourth and final question, we'll find that neither the 12, neither the 50 is a perfect square, so we have to simplify them each. Let's go ahead and try to simplify this numerator first. So I'm going to pull it off to the side here. So we have 5 root 12. Now, once again, we are trying to break down this 12. So let's find two factors that when multiplied equal 12. Again, we don't want any random numbers. One of those numbers has to be a perfect square. So what multiplies to 12? 2 times 6. But that's not a good pair because neither the 2 nor the 6 is a perfect square. Let's go to the next one. 3 goes into that 4 times, and that is our best pair because 4 happens to be a perfect square. So I'm going to rewrite this as 5 root 3 times 4. The square root of 4 is 2, which, hopped out. And of course, you multiply that 2 with the 5 that was already there. So the new numerator is 10 square root of 3. And now that we've finished working on the numerator, let's try to simplify this denominator. Once again, I'm going to pull it off to the side. First, let me move this out of the way. All right, so now we will have root 50. We will try to simplify that. Well, of course, there's an invisible 1 out here. I'm just going to use the dashed line to show that it's still there. Now, what two numbers do we multiply to get 50? We have 2 times 25, and we got lucky on the first try because 25 is a perfect square. The square root of 25 is 5. So we can rewrite this as 1 times 2 times 25. The square root of 25 is 5, which goes on the outside. This 5 multiplies the 1 that was already there. So we end up with a 5 root 2. Now, as we continue working this question out, you'll notice that the 5 and the 10, the whole numbers can be simplified, these right here, because 10 is divisible by 5. So we'll go ahead and simplify those, and 5 goes into 5 once, 5 goes into 10 twice. So we now have 2 root 3 over root 2. One big problem, though, that we just ran into is that in math, you're not allowed to leave your answer with a negative exponent. Not allowed at all. We have to do something called rationalizing the denominator. I know that sounds fancy and complicated, but all it means is you're going to try to get rid of the root on the bottom. And the way to do that is pretty simple. So let me explain how you would do that. So every time you have a root, you simply multiply by whatever the square root is. So we have a root 2, so it's going to have to be multiplied by itself. Root 2 times root 2. And if you do it on the denominator, you have to do that same exact thing for the numerator. Now you'll find that for the denominator, we have root 2 times root 2. These multiply to root 4. And the square root of 4 is simply 2, so our new denominator is 2, which means we have accomplished our mission and gotten rid of the square root that we weren't allowed to have. For the numerator, we have 2 root 3 times root 2. Once again, there's an invisible 1 here. So 2 times 1 is 2, and then root 3 times root 2 is root 6. And you'll find that, once again, these 2's do cancel out, which makes the final answer simply square root of 6. Now, to clarify, to get rid of a radical on the denominator, all you need to do is multiply the radical to itself. So for instance, if you had 3 over root 5, to get rid of this root 5, you would have to multiply it to itself. So times root 5 times root 5. And the top would be 3 root 5. The bottom would be root 5 times root 5, which is root 25. And we know that the answer to that is 5. So I think by now you're seeing a trend. It's that anytime you multiply a radicand to itself or a radical to itself, you just end up with a radicand. So root 5 times root 5 is just 5. Root 2 times root 2 is just 2. If you had root 70 times root 70, it would just be 70. And so in conclusion, multiplying radicals is pretty straightforward. You would just multiply the coefficients. For example, in question 2, we had 5 and negative 6 as our coefficients, and we just multiplied them. And then you also just multiply the radicands. In every case, you have to check to see if your new radicand, after you've multiplied, is in simplest terms. If it's not, then you have to move on to simplifying it until it's in lowest terms. Dividing radicals is also pretty straightforward. You would divide like you normally would, but the one thing that you cannot have is a root. You can have a square root as a denominator. So you have to rationalize. And rationalizing just means multiplying by whatever root you are trying to get rid of. Now, I know this lesson had a lot of pretty intense concepts. And if any of these concepts feel fuzzy to you still, that's okay. I understand. And all you need to do is just watch the video over and over again as many times as you need to. You can hit pause. You should actually hit pause and try working the question out on your own to see if you actually get the answer right each time you try to. And that'll conclude this video. Next, we'll look at how to rationalize more complex radicals.